Hello again. So welcome to questions 5 and beyond. I don't know how far I'll get in this video, but these questions start off about something called plate tectonics, or how plates move. And if you remember the pretest, there was those kind of out there geology questions. So it's like, what are the layers of the Earth? What do plates move or not? And plates, they move. The plates that form the outer layer of the Earth and the continents and all that jazz, they move. And that moving of plates is called plate tectonics. And there are a couple different ways plates move. Question 5 asks for you to describe 3 of the biggest and major, most common ways. So they are either transform plate boundaries, divergent plate boundaries, and convergent plate boundaries. And here's a little picture showing that. Now, transform plate boundaries are ones that go next to each other. So transform plate boundaries go next to each other. They just transform. They kind of go next to each other. So divergent plate boundaries, they go apart. They diverge. So divergent. Divergent do that. And convergent come together. So they start apart and they come together, or they're moving towards each other. So here, 2 plates are coming together. And this is mirrored. Okay, so 2 plates are coming together here. And one is going down and one's going up. And when it goes up, it makes like a mountain and a volcano. Yay. Here, 2 plates are moving apart. And that forms like a crack and a ridge. And then lava comes through and you get more lava stuff. This is how vents are most commonly formed, by the way. That's a spoiler for the next question. This and this, these 2 plates are again like, oh, I shouldn't look at that. But they are coming down. Like they are coming together, so they're convergent, and this one is going down. So yes. So convergent plates, divergent plates, convergent plates, and transform plates. Kind of hard to see, but here and here they're moving like side by side. So like the divergent ones, some are moving apart faster and some are moving apart slower. So that's why sometimes along here, see how this line doesn't line up here? That's because right there, they're moving side to side. So yep, that's the different types of boundaries. So transform plate boundaries are moving next to each other. Divergent plate boundaries are moving away from each other. And convergent plate boundaries are moving together. So moving towards each other, whatever. Yeah, open-ended questions that have really similar answers. Anyway, question 6 brings us back to hydrothermal vents. Along what type of plate boundary are hydrothermal vents normally found? Well, let's look at that. So hydrothermal vents are normally found, and it looks like it gets it's blah 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 blah. Hydrothermal vents are usually formed along the boundaries of divergent plate tectonic plates. And these 2 pictures here, I'm going to make this whole thing bigger. Let me just hit the present button. And once it loads, we do the thing. I believe in you. If I make noises, it'll go faster. Okay, so these red lines here are all divergent plate tectonics. And you'll see that there's like blue lines kind of speckled all over the place. Those blue little dashes and those blue chonkers here, those are all transform plates. So sometimes moving away, sometimes sliding by. The green bits are all convergent plate tectonics. So where plates are moving together. And keep in mind, this is a sphere, this is a circle, so it's really hard to kind of visualize what direction everything is going on a sphere. But yeah, these are the ones moving together. These are the ones moving apart. These are spaces where they're moving kind of next to each other. So let's look over here. All of these dots are known hydrothermal vent ecosystems. And you'll notice a lot of them, this one is like right around here. these guys are here. These are here. These are here. These are here. So far, they've all been on divergent plate tectonics, except these. These guys are here. See that? So not all of them are found on divergent plate tectonics, but a lot of them. A lot of them are found on divergent plate tectonics. So yeah, that's pretty cool. Yeah, that's what this slide is about. So yeah, divergent plate tectonics is what I'm going to write down here. Hello again. Hydrothermal vents are normally found along divergent. That's not how you spell divergent. Don't judge my spelling. Plate. Just divergent plates. That works. That's good enough. Okay, divergent plates. So question 7. Based on these 3 physics ideas shared on slide 8, what do you think is the biggest reason why everything isn't squished or crushed beyond all recognition by atmospheric pressure? So, this slide is scary. This slide has a lot of physics ideas. Okay, and it asks for one of the biggest ideas. So if you're going to play the text hunting game for this, it'll be rough. It'll be rough to play the text hunting game here. What I'd like you to do is I'd like you to read through these and get a pretty good idea of what they're actually all saying. So I'm going to read through them now in this video. So yay, this is my reading voice. To understand life in pressure, you need a pretty good idea about the physics behind it. There is some pretty advanced physics going on here, so take some time with this slide. If atmospheric pressure is at 14.5 pounds per square inch, why does an 10-inch table collapse? Shouldn't roughly 150 pounds be pushing down on it? Well, so that's because 10 inches square is 100, and 100 times... Anyway, so pressure doesn't work in one direction. Air pressure, atmospheric pressure works in all the directions. So let me go back to where I can see my face, and I'm going to try to show you this with my phone. So here's my phone. It's hanging out here, right? Yes, there's a lot of air pressure on here. And if there was that much air pressure and it was just pushing down on it, my phone would break. But it's not just pushing down. It's pushing up as much as it's pushing down. It's pushing to the side as much as it's pushing down. It's all pushing the same amount from every single angle, which is why the only thing when I drop my phone is gravity that lets it fall, because then it's just its own mass pushing it down, because air pressure is all around. Yeah, and if that absolutely makes zero sense, watch this video here. Click on it. Click on that link. It's a physics video. It'll explain the whole table thing in a pretty neat way, better than I can. So that's possibly one reason you could have as your favorite. These are all reasons, by the way. Another reason is why things don't just get squished or crushed beyond all belief under lots of pressure is because not everything gets squished, truly. So the only thing that actually gets squished is gas. So everything else other than gas, so solids and liquids, have a constant density. So clay, this post-it note here. This, I can squish it, I can roll it up, I can bend it, but this will always have the same amount of mass and the same amount of volume. Like, I can open up the papers, yes, but I didn't increase the mass of this stack of Post-its. There's still the same amount or mass of Post-its here, and they still occupy the same amount of volume. There's just more space between them. So things under atmospheric pressure, well, you can't compress something that's not compressible. And then lastly, this last physics idea, wouldn't gas still get compressed by the extreme pressure? And I'm like, yes. Right now, the air we're breathing is compressed air. It's compressed by the rest of the atmosphere. That's why there's enough air molecules hanging out and around for us to actually, get some oxygen in our blood. That's why altitude makes altitude not work. So, like, breathing is not easy in the altitude because the air is less compressed at higher altitudes. So air, yes, it is compressed. But the reason why it's not crushed beyond all belief is because air molecules push back. So in a balloon, If you squeeze the balloon, it won't squish instantly. That's because there's all those air molecules doing their thing inside the balloon. But if you squish the balloon harder, it'll eventually squeeze down. We'll talk more about this on the next slide, but something to put actually for answering question 7. So based on these physics ideas shared on slide 8, what do you think is the biggest reason everything isn't squished or crushed beyond all recognition by atmospheric pressure? And I'm going to write down kind of that last idea, because pressure is on all sides, and because objects push back. So it may not seem like it, but when I crush or push this solid, pushing back at me the same amount. I can feel it in my hand as hard as I push. It's one of Newton's laws. But slightly different with gases, because you actually can compress them, and the harder compressed the air, the more it will push back. That's why tire pressure is written in pounds per square inch, just like atmospheric pressure can be written in pounds per square inch. So at 1 atmospheric pressure, this air, anything like we put air in a cup, that air, if we put a cap on the cup and sealed it in the cup, that air is at this pressure. There's pushing back that hard. If we take that air in a cup and bring it down to the bottom of the ocean, the same amount of air will be there, except it will get crushed. That cup will get crushed because that air is not pushing back hard enough to not get crushed. Similarly, let's go to the next slide. This is not the next slide. This is the next slide. If you take something with air in it that is already pre-crushed and you take it up to the surface where there's less pressure on it, it will opposite of crush. It will become a blobfish. So this lovely picture of our friend the blobfish, I'm going to make bigger, is what happens when air compression just stops happening. Well, or you're meant for being at low pressure. You're meant for being at high pressure and then suddenly taken up to very low pressure. So this fish normally lives in 3,000 feet below sea level. It normally lives way at the bottom of the ocean. Well, not quite as deep as our geothermal vents, but pretty gosh darn deep. And if you bring it up to the surface really quickly, its balloon, its skin, everything in it that's compressible, so gas, not solids or liquids, expand because they're pushing out too hard. So this poor fish ends up looking like a blobfish. And these are 2 very, very good videos. I'm going to highly recommend you watch. They're linked, by the way. Oh, go back. Not here. The struggle is so real. Where's my shrink button? Oh, there's my shrink button. Neat. Okay. These 2 videos are both super good. This video will explain the fish quite well. This video will explain a human who deep sea dives without any sort of support. So yeah, you should definitely watch both of those videos. But when you do that, you're gonna watch it, and then you're gonna summarize it. So I'm going to kind of cheat here and say I chose to watch the video about the diver, and it was how much time do I have left? Not much. This video is about out of time. I will pick up with this. You guys can write a summary of the video. I believe in you. As long as it's 2% summary of the video, I believe in you. Go for it. Watch them both. They're both really good. This one's a TED Talk. This one's from the History Channel. Watch the videos. Yeah, write a summary? Yeah?